Welcome back, everyone. Today, we're doing something really exciting in this explainer. We are cutting through all the high-level buzzwords and all the hype to completely deconstruct the actual math and architecture of deep learning. If you've ever found yourself wondering how these systems actually compute under the hood, we're going to prove today that it's pure, structured, and honestly, incredibly elegant mathematics. By the end of our time together, you're going to see exactly how these massive architectures are built straight from the ground up.
So let's just start with the absolute most fundamental question, one that honestly gets lost in all that sci-fi hype you see online. What exactly is a neural network? We hear the term constantly, usually paired with some flashy graphic of a glowing blue brain, right? Well, let's strip away all those aesthetics for a minute and look at the mathematical reality.
And here is the big reveal. Straight from our source material, and I absolutely love this quote, "You already know what a neural network is. It's logistic regression." No, really, that's it. If you understand basic statistical regressions, you already hold the keys to the entire deep learning kingdom. A neural network is simply a mathematical function. More specifically, it's just a series of nested mathematical functions. It's a function inside a function inside a function. It's literally that simple, and yet it is unbelievably powerful. All right, here's our roadmap for today. Number 1, beyond simple regression. 2, the multilayer perceptron. 3, deep learning challenges. 4, CNNs and how computers see. And finally, number 5, RNNs for processing sequences. Okay, let's dive into this. Section 1, beyond simple regression, the foundations. Now, to really wrap our heads around these nested functions, we need to lock down 2 quick definitions. First up is the activation function. This is just a fixed, nonlinear mathematical function that gets applied to the output of a layer. Second is the fully connected layer. And this is exactly what it sounds like. It's a layer where every single unit receives inputs from every single unit in the previous layer. Keep those 2 concepts in your back pocket. Moving right along to Section 2, the multi-layer perceptron, the vanilla network. So let's see what those definitions actually look like in practice. If you look over on the far left, right there in the green circles, we've got our 2-dimensional feature inputs. And notice the logical flow here, moving left to right through layers 1, 2, and 3. Inside those blue, purple, and red rectangles, a linear transformation is happening. The inputs get multiplied by a matrix of weights, a bias is added in, and then boom, the result is passed right through an activation function. And because every single output from layer 1 connects directly to every input in layer 2, this right here is our fully connected architecture. But wait, let's talk about those activation functions for a second. Why do we even need them in the first place? Well, think about it. If we only used linear transformations, our massive, complex neural network would mathematically collapse down into just one giant, completely useless linear function. We absolutely need nonlinearities. The table here lays out the heavy hitters. You've got the logistic or sigmoid function, which squeezes values between 0 and 1. We've got TanH stretching from -1 to 1. And then there's the incredibly popular ReLU, which is super simple. It just outputs 0 if the input is negative, and if it's positive, it just passes the input right through. These functions, they are the absolute secret sauce. They are what allow neural networks to learn the incredibly complex, nonlinear patterns of the real world. Which brings us to Section 3, deep learning challenges, the vanishing gradient. Now you might be thinking, let's just stack these building blocks hundreds of layers deep. But when we do that, we hit a massive wall. See, to train a network, we use a process called backpropagation. And backprop relies on the chain rule from calculus to update the parameters. But if we use traditional activation functions like TanH, which spit out really small fractions, chaining them together becomes a total disaster. You end up multiplying tiny fractions by tiny fractions across dozens of layers. And what happens? The gradient shrinks exponentially until it literally vanishes. The earliest layers in the network just stop learning entirely. The whole thing stalls out. So how did we fix this? Because to trigger the deep learning boom, we desperately needed some clever mathematical bypasses. Well, that ReLU activation function we just talked about, that was a huge deal. It doesn't squash positive numbers into tiny fractions, which massively reduces that vanishing effect. The industry also came up with brilliant things like LSTMs and skip connections in residual networks to just let those gradients flow through unimpeded. And it's exactly these modern tools that finally allowed us to successfully train networks that are literally thousands of layers deep. All right, let's shift gears to Section 4, CNNs, how computers see high-dimensional data. Okay, so what happens if our input is a high-resolution image? A standard fully connected network would need millions of parameters for that. It's computationally impossible. So CNNs step in and conquer this by making a really smart assumption. Pixels that are close together represent this same local object. It's kind of like looking at a dollar bill under a microscope. You can't see the whole thing at once, so you gradually move your microscope left to right and top to bottom. Mathematically, we do the exact same thing. Step 1, we split the image into square patches using a moving window. Step 2, we slide a filter across that patch. And step 3, we calculate a dot product to sum the values up. Now, what's really interesting about this slide is exactly how this math plays out. Look at that grid setup. The larger one is our image patch. That smaller grid sliding over it is our filter, and it's looking for a specific local pattern, maybe something simple like a sharp edge. As this filter slides over the image, which is a mathematical operation called convolving, it multiplies the overlapping squares and then adds them all up. If it finds a perfect match, it spits out a really high number. A total mismatch, you get a low number. This is a brilliant operation because it drastically reduces the number of parameters we need to compute while still perfectly detecting edges, textures, and eventually entire complex objects.
But of course, real images in the real world have color, right? Which means they aren't flat grids, they are 3D volumes. Instead of a single flat matrix, a color image has 3 matrices stacked right on top of each other for the red, green, and blue color channels. But don't worry, our moving window technique scales up flawlessly. The filter just adapts. It convolves across all 3 of those channels simultaneously, crunching that entire volume down into a single output number before sliding over to the very next patch.
Moving on to our final section, number 5, RNNs, processing sequences, time and memory. So CNNs are undeniably incredible for static images, but what happens when we need to translate a spoken conversation or read a long sentence? Let's draw a hard line here so we're absolutely clear on the difference. CNNs handle spatial data, that's local image patches, completely frozen in time. RNNs, on the other hand, handle sequential data, time-based text and speech. The order of the data fundamentally matters here. And processing data over time means our network needs a massive upgrade. It needs a way to actually remember what it literally just saw a moment ago.
Unlike the feed-forward networks we've been looking at, RNNs create this memory by utilizing loops. And this brilliantly illustrates how it works. Notice how this network unfolds from left to right over time. At any given time step t, the unit receives not just the brand new input x, but it also receives the state, the memory, from the previous time step, t-1. By continuously combining new input with the previous state, the network actually maintains context as it chugs through a sequence.
There is a catch, though. Just like our early deep networks, basic RNNs start to forget things if the sentence gets too long. It's a long-term dependency issue. So what's the solution? Gated RNNs, specifically architectures known as GRUs and LSTMs. You can think of these kind of like bits in a computer's memory. They use mathematical gates that actively learn when to read, write, and erase or forget information. For example, if an RNN reads the word she at the very beginning of a massive paragraph, the gate learns to write that gender into its memory and keep it locked down safe. This completely bypasses that vanishing gradient problem we talked about earlier, allowing the network to correctly interpret the word her several sentences later. It's genius. We've journeyed all the way from basic logistic regression to these wildly advanced architectures that can visually recognize the world and sequentially remember complex human language. And as you've seen, it really is just beautifully nested mathematical functions. So I'm going to leave you with this provocative thought. If we can mathematically mimic spatial recognition with CNNs and sequential memory with RNNs, what fundamental human cognitive ability will nested functions conquer next? I mean, think about that. Thanks so much for joining me on this explainer today. Keep learning, and I'll catch you next time.